Thank you for the introduction. My name is Zhang, and together with co-author Wan Lixing and Chenglu Li, we are from University of Florida. I'm very pleased to be here to give this presentation. The title of my presentation is Predicting Students' Algebra 1 Performance Using Reinforcement Learning with Multi-Group Fairness. My presentation will include three main parts, some background information, and the methods we used, and some results we have got the last our future work. With the ubiquity of personal electronic devices and development of high-speed networks, especially during the epidemic around 2020, online learning has gained increasing popularity in K-20 and higher education settings. Studies have shown that online learning can support efficient, effective, scalable knowledge inquiries. There are also some challenges. One of its long-standing issues is the relative loose connection between students and teachers. With this factor in mind, researchers have shifted to using machine learning to provide automatic, actionable insights for teaching and learning. Numerous studies have successfully adopted machine learning to address educational issues, including predicting students' performance, decoding students' learning process, understanding student learning dynamics in online discussion forums. Although the application of machine learning have achieved promising results in education, research have paid attention to the problem of algorithmic bias in machine learning. Studies across many fields have demonstrated the algorithmic bias can occur in the decision-making process of machine learning. The most famous case is Emerson's hiring algorithm, and there are also some bias in educational machine learning. There are currently three areas of research focusing on mitigating or addressing algorithmic bias in education. The first research aims to conceptually operationalize and discuss bias in education and its implications. The second area steps further and conducts bias evaluation of machine learning model in education applications. Well, the first two research areas yield important findings, but however, they didn't provide concrete strategies to mitigate bias. Therefore, the third strand of research have emerged to fill the gap and have achieved preliminary success in single group debates. But however, in everyday life, students will have multiple identities which naturally characterize them as part of multiple groups. Enhancing model fairness with a single group cannot guarantee that the same fairness with multiple groups, which can impair the achievement of equity and equality in education with machine learning. Therefore, there is a need to develop models with multi-group to further the application of machine learning. This figure shows the multi-group problem. We can see there are two attributes, Hispanic indicator and FIL status. In the right chart, the single group distribution is the single group distribution. We can see they are really same distributed, which won't lead to unfair, but in the left chart, the multi-group parts, they are really differently distributed. and which easily lead to unfair in education. So the multi-group really matters. There are three approaches in debating, pre-processing, algorithm modification, and post-processing. In this experiment, we're using a pre-processing approach. We propose a scheme, a combined reinforcement learning model and machine learning classification model, which can effectively reduce model bias in multi-group. Then let's introduce the methods we use in this experiment. First, context and data. The data were collected from Algebra One Nation, a virtual learning platform. We collect students' ANID demographics and EOC exam results. Students were informed and parental consent received before we extracted the data. There are over 3 million learning log entries and nearly 900,000 in-platform assignment results from over 14,000 students. Table 1 shows the details and the variable description. We extract a total of 23 features from the dataset. To complete the classification task, there are 4 main tabs: information, personal information, logs information, assignment information, and academic performance. Table 2 shows the subgroup information. There are 3 sensitive attributes here, which are FRL status, which shows the economic level of students, race indicator, and Hispanic indicator. They produce 8 subgroups, and because group 1 and 5 are missing in our data, in subsequent experiments, we only consider subgroup 0, 2, 3, 4, 6, 7. We test 5 machine learning models in the classification part: KNN, SVM, naive Bayes methods. After testing, we found that the KNN classification and Gaussian naive Bayes algorithm perform better in accuracy, F1 recall, and precision score. And in the follow-up experiments, these 2 models were used for comparative experiments. Usually in a binary classification model, we use absolute between ROC area to measure the bias level of the prediction model. The difference between the 2 AUC reflects the fairness. Here, in order to adapt to multi-group and multi-classification problems, we perform fairness evaluation by calculating and comparing the macro average BPSN AUC of each subgroup. The BPSN definition is shown in this equation, and the smaller the range, the standard deviation, the variance AR, we can get better fairness level. The main use of the reinforcement learning model is adjust the training data in the basic logic of reinforcement learning. The agent learns through interaction with the environment, and the learning objective of reinforcement learning is to maximize the numerical signal, which generally refer to the reward. By learning what to do, which generally refer to the action. In this experiment, we use the reinforcement learning model based on the policy gradient algorithm, and we provide two reward schemes. One is apply fairness constraints, and accuracy constraint is not imposed, and the model approaches the most fairness level. The other is jointly controlled by accuracy and the fairness. This is the workflow of the experiment. Firstly, the reinforcement learning model scans the dataset and give a policy to update the training site. Then train the machine learning model with new training data and get rewards. This reward will return to the reinforcement learning model and used to train the reinforcement learning model. After iterations, we end up with the training site grouping strategy, which gets the best rewards, which means the best fairness level and better accuracy level. Then I will show some results of our experiments. This figure shows the experiment's loss, accuracy, and bias evaluation changes. We can see that as the number of iterations increases, the bias level of the data decreases significantly. However, at the same time, the data classification accuracy also decreases. Before 8th iteration, the decline is, but however, before 8th iteration, the accuracy decline is slower, and after 8th iteration, the continued adjustment of data increase the bias level. During this period, the degree of fairness will decline and accuracy rate will drop rapidly. We call this stage out of control period. We keep the training site adjustment strategy of the lowest point to obtain high accuracy and better fairness. This figure records the results using KNN as machine learning model. There are amount of 5 sets of data. Training data is the original data. Training data adjusted 1 and 2 are iteration without adding accuracy constraints. Training data adjust 3 and 4 are jointly controlled by bias level and accuracy. From the figure, we can see that our scheme can significantly reduce the bias level, whether because the range standard deviation variance are decreased significantly. And we can see although this process has a trade-off of accuracy, we can reduce the bias level within our acceptable accuracy drop by imposing accuracy constraints. This figure shows the results using Gaussian naive Bayes as machine learning model. By comparing, it shows the same results, which is same to the last figure. In addition, by comparing the two models, we found that although both models achieved the expected results, the experimental effect of KN group was better than that of Gaussian naive Bayes group because the bias level drops more and accuracy level drops less. The results demonstrated that our proposed model effectively reduced algorithmic bias in multi-group setting within our acceptable accuracy drop. The finding implied that there could be a paradigm shift from focusing on debarrassing on a single group to debarrassing multi-group in educational machine learning attempts. Through the introduction of the reinforcement learning model, we can effectively solve the bias problem, and the model can also better meet the invisibility of data. In the future work, we plan to introduce explainable artificial. At the same we plan to use explainable artificial intelligence to explain our experimental results. XAI is a set of processes and methods that allow human users to understand and trust the results and outputs created by machine learning. We will introduce the fairness check, the variable breakdown, the variable importance analysis to better prove fairness and better understand the factors of machine learning model to judge and connect with real life to better learn and analyze. Thank you, everyone. I would appreciate any comments and questions.